In this work, we present a learning from demonstration framework for multi-robot systems using interaction keypoints and soft actor-critic methods. Robots and multi-robot systems are being widely used today across various applications both in industry and household domains. However, most of these robots operate in rigid scenarios where programming the robot is done either with a pendant that has a GUI or it is done using code. And both these methods happen to be very rigid in how a human communicates with a robot through programming. As you can see in the video, it takes around 2 minutes to make a robot move from one position to another to pick and place an object in the industrial settings. Because of rigid programming, robots suffer from various consequences. The first is that most of these robots are impractical to deploy in dynamic and varied settings, which are often daily human environments. Secondly, these robots lack contextual understanding or reasoning because of the rigid nature of their programming. Furthermore, if the robot needs to be repurposed to a new application, it needs to be reprogrammed, which comes with a significant time cost and a barrier for the non-expert and the layman. We envision a scenario where robots can be taught much like how humans teach their fellow counterparts through demonstrations, where if a human shows two different types of tasks to robots, they can understand the interactions in the task, the key points, and various environmental artifacts, and figure out how to accomplish the task by learning from demonstration. Most of the related works cover two types of tasks, contact-based tasks and abstract behavioral tasks. These related works can be divided across their methodologies and the type of demonstrations they use. While most of these works work with demonstrations that include a more discrete set, there are very few methods that use vision-based demonstrations performed by humans which are very intuitive from a layman human point of view. Furthermore, most of these methods are also specific to certain tasks and scenarios and cannot generalize across multiple tasks and multiple environments. Before we begin, let us try to understand the nature of a task. So a task is given, such as assemble all the objects on the table. To accomplish this task, the robot has a set of primitive skills or a priori skills. A combination of these skills would allow the robot to basically accomplish the task. And these combinations would become the subtasks, where the first subtask could be go to object, which requires the read skill. The second subtask could be pick up object, which requires the pickup skill, and so on. The problem we are trying to solve is given a visual demonstration as a sequence of frames D, we would like a task policy that allows a multi-robot system to accomplish the demonstrated task. The proposed approach starts off with an input demonstration which is fed to a vision tracking module. This module keeps track of all the objects and robots in the environment, including object properties such as shape, position, and color. The output of the vision tracking module goes to the task policy inference module and the robot execution module. In the policy inference module, interaction key points are detected, which are key zones within the demonstration which signify the transition of robots from one subtask to another. These detected interaction key points are then used to classify skills using a decision tree. Once skills are classified, a task policy is obtained as a chain of multi-robot skills. Now, in a scenario where a new skill is detected, which is when the decision tree cannot detect a certain key point or a skill, in those scenarios, we use RL skill learning, which is also a RL practice module for the robots. These are mainly for contact-based tasks, which require more complex manipulations and collaborations between the multiple robots. Finally, once all skills are learned, the task policy as a chain of multi-robot skills is sent to the robot execution module, which allocates the respective robots to the respective subtasks and carries out the robot policy execution. Let's break down this approach one by one. The first assumption we make is that all the individual robots have a priori skills. And these are modeled skills that every individual robot can perform. Each a priori skill will precede and conclude with an interaction key point that denotes a transition from one skill to another. The interaction key points are defined based on the interactions in the environment. We identify three sets of interactions. The first are object-robot interactions, second are object-object interactions, and finally robot-robot interactions. These interactions are then modeled using the decision tree to detect skills. An example task policy is shown here, where given a human demonstration, the task is basically broken down into subtasks such as approach object, contact object, and RL skill, which is obtained through the RL skill training module, and finally retreat from object. In this scenario, approach, contact, and retreat are individual robot a priori skills, whereas the RL skill is a contact-based collaborative skill. Now, what is the need for skill training? The main need for RL in our work is essentially for cooperative contact-based manipulation tasks, and these tasks are often difficult to model using vision. The challenges in designing an RL module are essentially with the reward function. Since we're trying to generalize across multiple types of tasks, designing a general reward function is not trivial. We also choose a soft actor-critic for our implementations, and this is because soft actor-critic methods are very good at real-time implications. And they also allow for single critic and multi-actor networks. Our state space is essentially the image of the environment, along with all the robot and object positions and the interaction key points along the video. The action space are robot wheel velocities. The reward structure is divided into two parts. The first is a global reward, which is obtained through a binary decision classifier that is trained on goal scenarios. This would signify the reward for the entire team. The other reward that we have are local rewards, which are interaction key point rewards, which also help the entire system converge faster. The total reward is essentially the global reward along with the interaction rewards. The results show that the proposed method outperforms the baseline method, which is a naive reinforcement learning algorithm that tries to achieve multi-robot tasks. Furthermore, in the case of behavior-based tasks, our method can accomplish all these tasks from a single demonstration that is not noisy or corrupted. In the case of contact-based tasks, we require more demonstrations because of the nature of the decision classifier, but it is still under a few-shot learning paradigm. In the video, we start off with behavior-based tasks across different conditions where the robots and the objects are generalized to different positions. You can see that our method learns this from just one demonstration and understands the nuances of the task. Another behavior-based task is the leader-follower task, where the demonstration shows the robots lining up behind a leader. These are also tested across various starting and ending locations to allow generalizability for the framework. Finally, we show contact-based task as well, which is the object transport and the object sorting task. The object transport involves transporting an object from one location to another. The sorting task is a little bit more complex, where depending on the color of the object, different objects are sorted to different goal positions. We also conduct ablation studies on our reward design, where the proposed method is essentially the IK rewards and the classifier rewards combined. As the results show, we can see that the combined method performs way better compared to the other two methods. The classifier-based reward method works as an ulterior goal or a global goal, but this essentially slows down the entire process of accumulating rewards at the beginning. However, in the IK method, robots can be stuck at a local goal and not maximized towards the global goal, and that is why they perform even more poorly compared to all the three methods. To conclude, we present two contributions to this work. The first is a novel learning from demonstration framework for multi-robot systems that utilizes visual key points and soft actor-critic methods. This framework addresses a key gap in current research, where there are no multi-robot system frameworks for learning from demonstration that can handle both behavior and contact-based tasks. The second is that we evaluate our framework through real-time experiments on these diverse sets of tasks, demonstrating its efficiency in collaborative behavior and contact-based tasks. Furthermore, to show the significance of our research, we solved the two key problems that stay as barriers when transitioning from robots in industry to real-world settings. The first is that our system is not a barrier for the layman, where a human can communicate with our system using human-based demonstrations. The second is to reprogram a robot, you will just have to show a new demonstration to the system. And this would also be a significant cut down in a barrier, especially in the case of reprogramming time and also hiring a professional programmer to reprogram the robot. Thank you.